started quick. Like I said, I'm not going to go through everything in detail because, well, I got to get going. But we will go through it fairly quickly. So, number one, calculate the force of gravity on the spacecraft 12,800 kilometers above the surface of the Earth if its mass is 1,400 kilograms. Main thing to be careful with here, first of all, this one all the way through problem 5. So problems 1 through 5 are all going to use this equation right here. And remember that G is equal to 6.67 times 10 to the negative 11th. Now the thing to be careful of is that everything has to be in meters and kilograms because you're looking for newtons, you're looking for a force. So, like this one says 12,800 kilometers, that's actually 12,800,000 meters, plus you also have to include the radius of the Earth. So basically what you're looking at is something like this. All right, so you have the Earth, which we know to have a radius of 6.38 times 10 to the 6th, which is, you know, on your paper, plus it's an additional 12,800,000 kilometers. Okay, so your value for R for problem number 1 is actually going to be 638,000 plus 12,800,000. All right, so that's going to be your value of R. Plug in the force of the satellite. Plug in the mass of the Earth. Plug in G. You're done. The answer should be, for number 1, the answer should be 13,900.7 newtons. Number 2, there's 2 ways to go about number 2. You can go ahead and say, all right, well, if the mass is 115, and I know the mass of the Earth, and I know the radius of the Earth, and I know G, so I can go ahead and find the force of gravity. The much easier way, however, is to say, there we go. All right. The much easier way is to say, okay, what happens if the mass of the planet is 2.5 times Earth's? Well, if that mass goes up by 2.5, then that means the force of gravity is going to go up by 2.5. All right, and if that's the case, well, you know that the force of gravity on a 115 kilogram student is going to be 1,150 kilograms, so just multiply that by 2, or by 2.5. And when you do that, you're going to get an answer of 2,875 newtons. Number 3, the only trick to this is I forgot to include the mass of the student. Just go ahead and use 100 kilograms from the one below. It's really no different. Oh, there is one trick to this for number 3. The trick is you're looking for right as the student begins to move. So what that's telling you is if the force of friction is 100 newtons, that's telling you that this force of gravity here is going to be 100 newtons. And that wasn't the highlighter at all, but whatever. All right, so I just used 100 kilograms. If you use something slightly different, don't worry about it. It's fine. And that's going to give you 5.99 times 10 to the 12th newtons. Number 4 is the exact same problem. They just changed the numbers around. And that gives you 1.01 times 10 to the 11th newtons. And then number 5, again, exact same problem, just different numbers. And that's going to give you 65.03 newtons. Oh, and I'm sorry, these last 2 are not newtons. They are kilograms. All right, hold on 1 second, guys. All right, sorry about that, guys. Apparently I had a freshman think another teacher was in here, and he probably thinks I'm crazy for talking to a whiteboard in a room by myself. So, hey, now I've got that rumor going around about me. So, let's talk about number 6. A geosynchronous orbit is one where the satellite orbits the Earth with the same period of motion as the Earth on its own axis. How far from the center of the Earth is the satellite's orbit? All right, for this one, you have to use this equation here. And I warned you about this in class. Now, really quick, I'm going to show you this again. I showed you this once in class, but why not? All right, so where this equation comes from is, we know the equation for centripetal force is mv squared over r. Now remember, for a satellite in orbit, the centripetal force is provided by gravity. So I'm going to add an m sub s here for the mass of the satellite. And the force of gravitational attraction is going to be equal to g, the gravitational constant, times the mass of the Earth, times the mass of the satellite, divided by the radius squared. Well, hey, guess what? There's a massive satellite there. I'm going to cross multiply and get g, mass of the Earth, r equals v squared. That was weird. R squared. Now we cancel out an r. Now, the thing is, it's asking for the period. Well, we also have another equation we can use. The period is equal to 2 pi r over v. Okay, just double checking I rearranged that equation correct. It's normally v equals 2 pi r over t. But yeah, that should be fine. All right, so then, wait a minute. I think I did that right, but let's just check that one here. I need it in terms of anyway, so I don't know what I'm doing. All right, so 2 pi r over t. So here's the thing. What we're going to do is we're going to square this, which means v squared equals 4 pi squared r squared over t squared. And now we're going to take this whole thing, we're going to get and take this, and move that over into this v. So what that means is we have g, mass of the Earth, equals 4 pi squared r squared over t squared times r. Hey, guess what? That makes this cubed. And then final step, we're going to go ahead and solve this for t. So when we cross multiply here, we're going to get t equals 4 pi squared r cubed over g, mass of the Earth. And we're going to take the whole square root of that, which if you move this part out, it gives you t equals 2 pi radical 3 cubed gravitational constant times mass of the Earth. And that's a horrible e, but we'll live with it. Which, by the way, is that equation right here. All right, so that's where it comes from. Now, I know we saw that in class. None of this is important. You don't have to do it on the test, but at least you know where it comes from. Just combining the circular motion with gravity. All right, so now what this question actually asks is what, if I grab the right paper, a geosynchronous orbit. Okay, so we know the period is the same as the rotations of the Earth. Well, to figure that out, remember, this all has to be in SI units, which the SI unit of time is seconds. So what we have to say is the Earth rotates in 24 hours. There are 24 hours in a day, 60 minutes per hour, 60 minutes per second, which means there's 86,400 seconds per day. 2 pi, r cubed, gravitational constant, and times the mass of the Earth, which is at the top of your page. Done. Solve for r. I'll leave the algebra grunt work to you, but you should get an answer of 7.33 times 10 to the 24. It's going to be r, so that's meters. And that's, remember, from the center of the Earth's orbit. So if it asks you how far above the surface, you've got to subtract out the radius of the Earth. All right, let's see here. Number 7, same thing. The only difference is it tells you that it's placed 16,090,000 meters above the Earth's surface. That is not r. That's r. Remember, it's from the centers of the object, so you have to include the radius of the Earth. So, and now it asks you, a satellite, how fast is the satellite orbiting? That's not period. But what we're going to do is we're going to come back to over here. We're going to go back one step, go forward one step, back to when we had this derivation. We're going to use an easier derivation here. All right, what we're going to do is go back to this right here. All right, so this was the step before we plugged in v squared, before we did anything like that. Because look, we've still got everything in terms of v right there. So what we're going to do is say, let's see if I can remember it without going back, because my memory's shot today. So that derivation left us with g m sub e equals v squared times r. Now it's asking us for velocity, so I'm just going to rearrange this. So that gives us v equals g mass of the Earth over r square root thereof. Okay, look, here's your radius. Plug that on in. You know g, you know the mass of the Earth at the top of the page. Plug it in, get a number, and you should get, where did I put it? 4,200, and I think that's 9. I can't read my own handwriting. 6.67 meters per second. Next, number 8. Hubble telescope orbits Earth 596,000 meters above the surface of the Earth. What's its period and its tangential velocity? Again, in this case, r is going to equal 6,380,000. So what you're going to get is you're going to use both equations. First, you're going to start off here for its orbital period. And then you're going to shift on over into this for its orbital velocity. All right? Oh, sorry. So going back to the radius, it's going to be the radius of the Earth plus the 596,000 that the satellite orbits. Now you know r. You know r here. G and me are both constants that you are given. Plug them in. Find the answers. The period should equal 45,833 and 100.46 seconds. Your orbital velocity should be 4,555.22 meters per second. Last one, number 10. And then we are thankfully done. All right, so guys, this is a very, very basic circular motion problem. Oh, I'm sorry, I forgot number 9. That's probably helpful. All right, so number 9, a spaceship to orbit a planet with a mass 8 times 10 to the 20th kilograms. How far from the planet's center must the ship travel if it is to travel with a velocity of 10,000 meters per second? So, once again, we're talking, it has formed the planet's center, so you don't have to worry about the planet's radius, which is good because you're not given the planet's radius. So, again, it's just asking for, it gives you velocity. So, we had, I'm just going to leave this in terms of this, we're solving for the radius. So we had this equation solved out for the radius, gives us g mass of the Earth over v squared. It gives us velocity is 10,000. We know g, we know me. Plug it in, get r. You should get a result of 533.6 meters. So that better be a pretty dense planet. Last one, number 10. Very basic circular motion problem. You know the mass of the child, so you know mass equals 35 kilograms. It's 3.2 meters from the radius of this carousel, and it has a tangential speed of 2.6 meters per second. Well, what's this centripetal acceleration? We've only got one equation. All right, plug them on in, so you get 2.6 squared over 3.2, which should give you a centripetal acceleration of, if I can find it on here, 2.11 meters per second. Now, to find force, it's the exact same thing. Force centripetal equals mass times v squared over r. Well, hey, guess what? This v squared over r is right what we found there. So just take your answer and multiply it by the 35 kilograms, that's their mass. And that gives you 73.94 newtons. All right, good luck tomorrow. If you've got any questions, just save them. We'll do the best we can talking over Friday. Hopefully, I should have this graded, and we will go over the test on Friday. We'll watch a little episode of Mythbusters or something to give you a little break going into the week. And then on Monday, we are going to start on work and energy, which should be a little bit more exciting. We get to actually do labs. That's exciting. All right.